Welcome back, everyone, to another explainer. I am absolutely thrilled to have you here today because we're going to tackle one of the absolute coolest and honestly trickiest challenges in engineering, modeling complex physical systems. We're skipping the basic stuff today and diving right into advanced step response methods. So, if you're the kind of person who loves taking messy, unpredictable real-world dynamics and wrestling them into clean, controllable mathematics, well, you are in the exact right place. Today, we're going to break down the specific formulas and graphs you need to finally tame these wild systems. Let's get into it.
All right, here is our roadmap for this explainer. 1. Enhancing model accuracy. 2. Extracting 4 parameters. 3. The integrator special case. And finally, 4. Unified identification methodology.
Okay, first, let's establish our baseline. Take a look at this classic S-curve step response right here. When we apply an input to a standard system, you know the drill. There's usually a tiny bit of a delay, it ramps up, it might overshoot just a little bit, and then it settles into this nice, flat, predictable steady state. We've all seen it, right? And we all know how to model a basic version of it. But what happens when the real-world system you're actually trying to measure is super complex, and a simple first or second order model just doesn't fit this curve tightly enough? I mean, what then? We need a lot more flexibility.
That brings us to Section 1, Enhancing Model Accuracy, where we look way beyond those standard models. So the secret here lies in something called degrees of freedom. I want you to think of degrees of freedom as your engineering tuning knobs. A basic model, it might only have 2 knobs, say a gain and a time constant. But if your system is highly complex, simply turning just 2 knobs is never going to get your mathematical curve to perfectly overlap with your messy real-world data curve. By introducing additional tuning parameters, specifically K, L, T1, and T2, we are basically giving our model the flexibility it desperately needs to achieve a far, far more accurate approximation. It's a total game changer.
Let's look at how this works. Focus your eyes on that transfer function, g of s, right there in the middle. Up top, we have our gain, k, and our dead time, L. Then, down in the denominator, we've split our dynamics into 2 separate time constants, T1 and T2. This right here is our 4-parameter model. But, how do we actually find these values? Well, if you check out the strategy box on the right, it lays out a strict 2-part process. The first part is graphical estimation. Believe it or not, parameters k and l can actually be estimated directly by just eyeballing the step response graph. But part 2, algebraic extraction, yeah, that is a bit trickier. Parameters t1 and t2 cannot be eyeballed. You literally can't just find them on a graph. They demand a highly specific numerical approach using 2 precise data points from our curve.
Which brings us to Section 2, Extracting 4 parameters. Let's dig into that algebra. If we're actually going to extract T1 and T2, we need anchor points. We need a place to start. And in this specific methodology, the absolute magic numbers are 0.33 and 0.67. We are going to evaluate our system's response at exactly 33% of its final value and 67% of its final value. These are our mathematical balance points.
All right, focus in on the graph on the left for a second. Notice those dashed red lines? On the vertical amplitude axis, we find 0.33, and then we literally draw a line over to our curve and then straight down to the time axis. It hits at exactly 6.5 seconds. Then we just do it again for 0.67 on the amplitude, trace over, and down, and boom, we hit 8.9 seconds. Also, take a close look at where the curve actually begins to rise from 0. It is not at time 0, it's over at 4.3 seconds. That right there is our implicitly extracted dead time, our parameter L. Okay, now move over to the math on the right side. We take the specific time values, the 6.5 and 8.9, and plug them directly into our massive step response equations alongside our amplitude values of 0.33 and 0.67. We also toss in our extracted dead time, L, as 4.3. And you know what that leaves us with? Just 2 equations and exactly 2 unknowns, T1 and T2.
Now, before anyone starts sweating over trying to isolate T1 and T2 by hand with a pencil, I want to highlight this absolutely crucial engineering note from our source material. Finding T1 and T2 requires solving a nonlinear equation, which necessitates a computer. Phew! Modern estimation methods use computers directly for this step. Your only job is to set up the architecture, extract the precise coordinates from the graph, plug them into the framework, and just let the software crunch the nonlinear algebra to spit out T1 as 0.93 and T2 as 3.2. Let the machine do the heavy lifting. So you might be wondering, why go through all this effort? Why not just stick to a simpler model?
Well, because doing it this way mathematically guarantees that your resulting transfer function perfectly matches the real system's response at those discrete chosen points. You are literally forcing the mathematical model to tether itself exactly to the reality of the physical system at the 33% and 67% marks. It ensures an incredibly robust, rock-solid fit.
All right, let's shift gears to Section 3, the integrator's special case. Let's talk about systems that just refuse to settle down. Think about this for a second. What if the system never reaches a steady value? We literally just spent all this time building a beautiful 4-parameter model based entirely on finding 33 and 67% of a final steady amplitude. But if the amplitude never stops rising, you don't have a final value. You don't have an S-shape at all. So our entire previous toolkit just became completely useless. This visual brilliantly illustrates that exact nightmare scenario. On the left, we've got a unit step input, but instead of settling into a nice S-curve, it just ramps up and keeps going. It's an infinite incline. This is an integrator system. Now notice the mathematical derivation on the right. Our transfer function, g of s, looks way different now. We have a solitary s in the denominator multiplying the time constant term. That s is the integrator element. Because the curve never flattens out, we obviously can't extract parameters the old way. Instead, we have to evaluate the linear asymptote of the curve, that straight line it eventually becomes. If we trace that straight dashed line backward, down to where it physically intersects the time axis, it hits at exactly the point L plus t, meaning dead time plus time constant. And the slope of that straight line? That slope is our k, our velocity gain. We then take that highly specific point in time, L plus t, and evaluate our function right there. That yields the beautiful algebraic shortcut you see down at the bottom. T equals the amplitude at L plus t multiplied by Euler's number e divided by our slope k.
Okay, it's really essential we don't get our wires crossed here. In these specific, non-S-shape integrator models, K is no longer a final steady state gain, simply because there is no steady state. K is now the velocity gain. It's literally just the slope of the runaway incline. T, meanwhile, remains our time constant, which is a measure of the system's dynamic lag, and we mathematically pull that right from that L plus T intersection point we just found. Moving on to Section 4, Unified Identification Methodology. Let's put this structured approach together. Whenever you are faced with a brand new, completely unknown physical system in the real world, you can basically just follow this exact 3-step playbook to model it. Step 1 is always your diagnostic check, Step 2 is your graphical extraction from the data, and Step 3 is your algebraic calculation. Let's actually trace this path together on the flowchart right here. Step 1, you apply your step input and you observe. Does it lack an S-shape? Does it completely fail to reach a steady state? If yes, check, you apply the integrator model. Moving down to Step 2, you observe that infinite incline, you measure the slope of the linear asymptote to find k. Then, you trace that asymptote down to the time axis to find the intersection point L plus t. Finally, in Step 3, you move away from the visual graph and jump into the algebra. You take the amplitude of the curve exactly at that time, L plus t, multiply it by e, and divide it by your extracted slope k. And boom, you have just calculated the exact value of the time constant t. Once you have t, well, since you already derived the value of L plus t from the graph earlier, finding your dead time L is just simple subtraction. Just like that, you have completely mapped an unstable system.
Which brings us to our final big thought for this explainer. How does this mathematical bridge actually empower us to control previously uncontrollable unstable systems? Well, by providing a rigorous step-by-step way to turn runaway physical forces into known algebraic variables, we transition from just observing chaos to engineering actual control. Whether you're dialing in 4 degrees of freedom on a stubborn, messy S-curve or using asymptotes to finally tame an infinite integrator, the visual data always holds the key to the algebraic truth. Thank you so much for joining me on this deep dive. Keep examining those graphs, keep turning those tuning knobs, and I'll catch you on the next explainer.